Hello everyone. So in this first pre-lecture tutorial of chapter 16, we're going to simply have an introduction to acid-base chemistry. As you're about to read in the first part of chapter 16, there are a number of different ways to define what an acid is and what a base is. Primarily, we're going to be focusing on the Bronsted-Lowry definitions of acids and bases in this tutorial, though we will be discussing the Arrhenius definition in class at the beginning of the chapter, and also towards the end of the chapter we'll be discussing the Lewis definitions of acids and bases as well. But for now, let's focus on the Bronsted-Lowry definitions of acids and bases for this particular tutorial. So, in essence, the very first thing that we should do when we're trying to understand acid-base chemistry is have a clear idea of what acids and bases do. And so let's take a look at this example equation that I've provided on this slide. And so if you take a look at what's going on in this particular reaction, there is a proton on this species that's actually being donated to the water. When that occurs, on the product side, I'm left with a fluoride ion and this species, H3O+. H3O+ is referred to as the hydronium ion, or sometimes it's referred to as a hydrated proton. And essentially, for the purposes of acid-base chemistry, hydronium ions and protons are considered to be essentially equivalent species. And so, since the HF is actually acting as a proton donor, then we consider it a Bronsted-Lowry acid. Okay, whereas the water is actually acting as a proton acceptor. And so the water is acting as a Bronsted-Lowry base. Okay, now if you notice, this fluoride ion represents the remainder of the species of the HF once the proton is actually donated. And so because of that, the F-, or the fluoride ion, is considered to be the conjugate base of HF. Now again, HF, we know when it's an aqueous solution, is actually referred to as hydrofluoric acid. And so it should be of no surprise that hydrofluoric acid behaves as an acid. And now we know that after donation of the proton, the fluoride ion would be considered to be the conjugate base of hydrofluoric acid. Now, the species that is formed after a proton is accepted is referred to as a conjugate acid. So basically, the H3O+, or the hydronium ion, would actually be the conjugate acid to water, and water's acting as a Bronsted-Lowry base in this particular acid-base reaction. And so one of the important skills that we need to develop when evaluating acid-base chemistry is identifying acids and bases, and obviously the conjugate acids and the conjugate bases to those acids and bases within a given acid-base reaction. And so let's take a few examples of those. All right, here we have the bicarbonate ion. Okay, and it's going to be reacting with water. For these exercises, the equal sign represents an equilibrium. And I'm going to get carbonic acid and the hydroxide ion. And so what's happening here is one of the hydrogens from the water is actually being donated to the bicarbonate ion. And so since water is acting as a proton donor, then water in this case is behaving as a Bronsted-Lowry acid. The bicarbonate ion is accepting a proton, and so it would be behaving as a Bronsted-Lowry base. Looking at the product side, the carbonic acid is the conjugate acid to the bicarbonate ion, which is acting as a base, and the hydroxide ion is the conjugate base of water, which is acting as an acid in this particular reaction equation. Let's do the second example. Okay, here I have HCN, and so we know that is hydrocyanic acid, and if I have it reacting with water, I'm going to get H+. Now in this case, H+, as we said earlier, is equivalent to H3O+, and we're also going to get cyanide ion. And so what's happening here is that a proton from hydrocyanic acid is being donated to water. And so since the hydrocyanic acid is acting as a proton donor, then it is acting as a Bronsted-Lowry acid in this equation. The water is acting as a proton acceptor. Okay, so that makes it a Bronsted-Lowry base in this reaction. Now, if we look carefully in terms of what's on the product side of the reaction, the hydronium ion, or the hydrated proton, is actually the conjugate acid to the water, which is acting as a base. Meanwhile, the cyanide ion is what remains after hydrocyanic acid donates its proton, and so that makes the cyanide ion the conjugate base of hydrocyanic acid. Okay, let's do the final example on this slide. I have ammonia reacting with water, and that's going to give me the ammonium ion and a hydroxide ion. And so what's happening here is a proton is going to be donated by the water to the ammonia. Since water is acting as a proton donor, then that makes it a Bronsted-Lowry acid. Since ammonia is accepting that proton, it's acting as a Bronsted-Lowry base. Looking at the species we have on the product side, the ammonia is what we form when the proton is accepted by ammonia, and so as a result, it's considered to be the conjugate acid of ammonia. The hydroxide ion, in turn, is the conjugate base of water, since it's the remaining part of the water once the proton has been donated. Now, we're going to discuss in class how these conjugate bases and conjugate acids compare to each other in terms of acid-base strength, and also correlate that to how acid-base equilibrium might be shifted to one side of the equilibrium or the other in class tomorrow. But I wanted to call your attention to the fact that water's behavior is a bit unique. If you take a look within these three examples, here's water. And if you notice, water actually has the ability to act as both an acid as well as a base. And water's interesting acid-base properties don't just end there. Water is actually capable of interacting with itself to give hydroxide ions and hydronium ions. Now, to sort of break this down further, this is a figure out of your book, and basically the figure shows that we have the donation of a proton from one water molecule to the other. So that makes the water molecule on the left-hand side of the reactant side of the equation the Bronsted-Lowry acid in this case. The second water molecule is accepting a proton, so that makes it a Bronsted-Lowry base. And so the hydroxide would actually be the conjugate base of the water molecule that's behaving as an acid, and the hydronium ion would actually be the conjugate acid of the water molecule that's acting as a base. Now, this ability for water to act as both an acid and a base has a name. Basically, we call species like water that have this property, we call them amphiprotic. Okay, those species that can sort of behave both as acids and bases depending on what other species they happen to be interacting with. Now, this also creates an interesting quantitative relationship, because if you notice, the equation for this process is an equilibrium process, and so we can write a K value for this. And again, remembering our principles that guide the law of mass action when it comes to heterogeneous equilibrium, you should be able to reason out that the equilibrium constant for this process should be the hydronium ion concentration multiplied by the hydroxide ion concentration. Since this applies to the autoionization of water, this particular equilibrium constant has a special designation. We call it Kw. And what it allows us to do is it allows us to actually calculate either the hydronium ion concentration or the hydroxide ion concentration, provided we know the value of Kw. And as it turns out, at 25 degrees Celsius, the value of Kw is simply 1.0 times 10 to the negative 14th. And so we can use that relationship to actually run calculations. For example, suppose that I know that I have a solution that has a hydrogen ion concentration of 3.9 times 10 to the negative 3rd molar, and I want to calculate the hydroxide ion concentration. Again, assuming that this solution is at 25 degrees Celsius, then I can use my relationship for Kw. Kw is H3O plus my hydronium ion concentration times my hydroxide ion concentration. Now again, recall the hydronium and hydrogen are considered pretty much equivalent in terms of acid-base behavior. So we could also consider this the proton concentration multiplied by the hydroxide ion concentration. And again, assuming that we're at 25 degrees Celsius, that means that this is 1.0 times 10 to the negative 14th. So if I want to calculate the hydroxide ion concentration, all I need to do is take Kw and divide the hydrogen ion concentration. And if I do that, that's 1.0 times 10 to the negative 14th divided by 3.9 times 10 to the minus 3rd. And if I do that math, basically I get a hydroxide ion concentration of 2.6 times 10 to the negative 12th molar. Now, when it comes to solutions, all right, if I have a concentration of hydroxide ion that's equal to my concentration of my hydrogen ion, then we consider that solution to be neutral. Okay? At 25 degrees Celsius, that means that each of those concentrations, the hydroxide ion concentration and the hydrogen ion concentration, should each be 1.0 times 10 to the negative 7th molar. So if I have a hydrogen ion concentration in a solution that's greater than 1.0 times 10 to the negative 7th molar, then that would mean that my solution is acidic. But if I have a hydrogen ion concentration that's less than 1.0 times 10 to the negative 7th molar, then we consider that solution to be basic. Right? Correspondingly, the hydroxide ion concentration for an acidic solution should be less than 1.0 times 10 to the negative 7th molar. For a basic solution, however, the hydroxide ion concentration should be greater than 1.0 times 10 to the negative 7th molar. Okay, so we're going to take some time in class to introduce these basic principles of acid-base chemistry before moving on. So work on the follow-up assignment, and if you have any questions, by all means email, or if not, bring the questions up in class, and I'll see you then. All right, have a good night.